The observatory has opened an endless test track. A capsule accelerates under constant drive, while its resistance system pushes harder as the speed rises. After 4 seconds, it reaches 37.9 meters per second. After 8, 51.9. After 12, 57. After 16, 58.9. It keeps speeding up, but each gain is smaller than the one before. Mission Control has one question. If the test could continue without end, would the capsule cross 60 meters per second, or settle closer and closer without reaching it? To answer, we need to look toward infinity. A limit near a number asks us to zoom in around one input. A limit at infinity asks us to travel the other way, to follow the graph farther and farther out. The symbol x approaches infinity does not name a final x. It gives a direction. Choose larger inputs, then larger ones still. We watch what the outputs do along that journey. If they can be forced as close as we want to one fixed height, simply by traveling far enough, that height is the limit at infinity. Start with the simplest decay, 1 divided by x. At x equals 1, the output is 1. At 10, 1/10. At 100, 1/100th. At 1000, 1,000th. Multiplying the input by 10 divides the output by 10. The graph never needs to arrive at 0. Its remaining height can be made smaller than any tolerance we choose by moving far enough to the right. So as x approaches infinity, 1 over x approaches 0. The line y equals 0 describes the graph's far right destination, so it is a horizontal asymptote. But an asymptote is not automatically a wall. Raise the destination to 3 and let the graph wobble around it with a shrinking amplitude. The curve crosses y equals 3 again and again, yet the crossings tighten toward the same height. Far enough out, every crest and trough fits inside any corridor around 3. Crossing the line does not break the limit. End behavior, not barrier behavior, is what matters. Complicated formulas become simpler when we look far enough away. Consider 2x to the 4th minus 3x squared plus 7. Near the origin, all 3 terms visibly shape the graph. But compare every term with x to the 4th. The constant becomes 7 over x to the 4th. The quadratic becomes -3 over x squared. Both ratios shrink towards 0. On the far scale, only the leading term keeps its relative size. The lower power terms have not vanished. They have become negligible compared with x to the 4th. Now put 2 growing expressions into a ratio. In 5x plus 2 divided by x squared plus 1, the numerator grows roughly like 5x. The denominator grows like x squared. The denominator wins the race. Divide every term by x squared, the strongest denominator power. The numerator becomes 5 over x plus 2 over x squared. The denominator becomes 1 plus 1 over x squared. Every reciprocal piece fades toward 0, leaving 0 over 1. The whole ratio approaches 0. What if the strongest powers match? Take 3x squared minus x plus 4 divided by x squared plus 5x minus 2. Both top and bottom grow like x squared. After dividing by x squared, the lower power pieces become reciprocals and fade. The numerator's surviving coefficient is 3. The denominator's is 1. The ratio approaches 3. Equal powers do not cancel into mystery. They expose the ratio of their leading coefficients. Now let the numerator grow faster. X squared plus 1 divided by x plus 1. There is no finite horizontal destination. But the graph is not shapeless. Polynomial division separates it into x minus 1 plus 2 divided by x plus 1. The reciprocal remainder fades towards 0. So the curve draws closer and closer to the slanted line y equals x minus 1. Toward positive infinity, the output rises without bound. Toward negative infinity, it falls without bound. The useful asymptote is slanted, not horizontal. Infinity has two input directions. Positive infinity looks far to the right. Negative infinity looks far to the left. Even powers point the same way at both ends. X to the fourth rises left and right. Odd powers reverse direction. X cubed falls on the left and rises on the right. A negative leading coefficient flips those directions. End behavior is controlled by the leading coefficient, the leading power, and which horizon we follow. Not every bounded graph settles. Sign of x keeps oscillating between -1 and 1 with the same amplitude forever. No matter how far we travel, it never stays near one fixed height, so its limit at infinity does not exist. Now divide by x. The oscillation remains, but its envelope shrinks between -1 over x and +1 over x. Both walls approach 0. The trapped wave must approach 0 too. Motion can continue forever while its amplitude converges. Return to the test capsule. Its idealized speed is 60 times 1 minus e to the -t/4. As time grows, the exponential term e to the -t/4 decays towards 0. The remaining factor approaches 1, so the speed approaches 60 meters per second. In this model, the capsule never crosses 60 at any finite time, but it can come as close as a chosen tolerance demands. This is terminal speed, not a final moment on the clock, but a long-run balance encoded by a limit. We now have two ways to use a limit. Near a finite input, we zoom in and ask what nearby values agree on. Toward infinity, we travel outward and ask what long-run behavior survives. A vertical asymptote comes from outputs becoming unbounded near a finite input. A horizontal asymptote comes from outputs approaching a finite height while the input becomes unbounded. A slant asymptote records a simpler moving track whose remaining difference fades away. Leading terms reveal these horizons. Squeezing can reveal them even when a graph keeps oscillating. Soon, Derivatives will give us another way to compare growth. Only after that will L'Hopital's rule make sense. For now, remember the central question. Far enough along the road, what behavior can no longer be escaped?